Okay, yeah, thanks for the introduction, and hi everyone to those of you who haven't met me yet. My name is Lars. I'm a postdoc at Alfred Wegener Institute, and I'm very happy to be here today and have this opportunity to talk about my ongoing research that I've conducted together with all the collaboration partners listed here on the slide. And I would like to start by quickly providing you the motivation why we are interested in this research topic. So first of all, I think it is fair to say that over the recent years, a lot of studies have analyzed how cyclones interact with the sea ice cover in the Arctic and found that these cyclone events are an important driver of short-term sea ice variability in the Arctic. However, all of these studies have mostly treated these cyclones as individual separated events, which also act independently of each other on the sea ice cover. And at the same time, we know, mostly from studies focusing on the mid-latitudes, that we can expect particularly strong surface impacts, for example, precipitation or wind damage, if several extreme weather events, such as cyclones, atmospheric rivers, occur quickly after each other, which I will also refer to as temporal clustering on the next slides. And the idea now of our current work is to combine both of the previous points and analyze if temporal clustering of cyclones also occurs in the Arctic, and if so, if this is related to particularly strong impacts on the sea ice cover. And before we start diving too deep into this topic, I would like to show you an example of 3 intense cyclones indicated by these sea level pressure contours here that crossed the Barents Sea in a time frame of about 2 weeks. So that means they were traveling there rather quickly after each other. And the panel to the left shows you actually that we have quite strong cyclonic winds that occurred close to the surface during each of these cases, something like 15 to 20 meters per second. And then we also had an advection of a comparatively warm air mass here on the eastern flank of these cyclones into the Arctic. And since both of these factors, the high wind speeds and the higher temperature, can potentially impact the sea ice cover, I would like to show you the respective changes in sea ice concentration here on this slide. And here by the plot above shows you the base state, how the sea ice concentration field looked like before the cyclones arrived. And then down below you can see how strongly the regional sea ice concentration values changed during these 2 weeks of cyclone passages, with a pronounced decrease in sea ice concentration here in the eastern part of the domain and an increase in the western part of the domain. And we can get some further insights into this if we just plot the time series of mean sea ice concentration for this pink box that I included here. So this is just one example region that I've chosen. And then we can see how this develops. During each of the cyclones, the sea ice concentration goes down a bit further. And altogether, we have a quite strong impact on the sea ice cover for this case in February 2020. And now, of course, the question is, since this is only one case that I've shown you, if we can also analyze this statistically, and that's actually what we are trying to do in our current work. Quickly walking you through the database, we have conducted this analysis based on the ERA 5 atmospheric reanalysis. We took the sea level pressure fields with a 6-hourly temporal resolution and applied a cyclone tracking algorithm. And then we mostly focused on 2 time periods. The first one is 2000 to 2024, and then we can compare this also to an earlier time period, 1979 to 1999, so that we can also analyze if these clusters and their sea ice impacts have changed recently. And all the results that I want to show today are grouped in these rather broad seasons: cold season defined from October to February and warm season from April to August. But we have also conducted some further analysis looking at this on a monthly basis. As for the cyclone cluster detection itself, here we decided to go with a maximum allowed time gap of 48 hours between 2 cyclones. So that means, as also indicated here, whenever there are 2 cyclones after each other, we check if the time gap criterion is fulfilled, and if so, then we group them into a cyclone cluster, and if not, we cut the event and say, whenever there comes a new cyclone, that's really a new separate event. And so as you can see, today is about temporal clustering of cyclones. Just to say that, to avoid confusion, there's no spatial clustering of cyclone tracks involved in this analysis. Yeah, this method gives then the following spatial distribution of cyclone cases. To the left, you can see that the cyclone clusters of 2 or more grouped cyclones occur across the North Atlantic storm track region, basically. And also here, west of Greenland in the Baffin Bay, we can find some of these cases. And in contrast, the solitary cyclones, they occur rather broadly distributed across the Arctic and have maximum values here over the Eurasian and American continent. And yeah, you can also see by the brighter colors that in general we have more solitary cyclone events than clusters. But since actually each of these clusters represents several cyclones at once, I also calculated the rate of all cyclones which are part of a cyclone cluster, and that reveals a quite interesting regional contrast with very high clustering rates, something like 60 to 80% actually in the Barents Sea and yeah, in general across the North Atlantic storm track here, and rather low values in the Pacific marginal seas of the Arctic Ocean. And if we move on to the warm season, the most distinct feature here is that the number of cyclone clusters goes down, particularly here in the North Atlantic, and that means also the clustering rates of all the cyclones fall to something like 50%. A next thing that I would like to say about these clusters is how the intensity looked like, because we know that the intensity of cyclones is correlated to the strength of their sea ice impacts. And that means if I want to compare both of these subsets, I should first check if they are of roughly equal intensity. And as you can see, I think for the cold season, this works out for some regions here in the central Arctic Ocean quite well. Specifically here over the North Atlantic, though, we see that the clustered cyclones are a bit more intense than the non-clustered cyclones. And if we move on to the warm season again, this difference actually becomes even stronger, even though all the cyclones become weaker. So this is a quite known feature, I would say, based on the cyclone climatologies that are out there. We know that summer cyclones are just weaker pronounced. And yeah, this is maybe interesting, but it's focused here on the Barents Sea and the open water areas. So I would say over the sea ice covered parts of the Arctic Ocean, we should be able to compare our sea ice impacts since the intensities are rather similar. And with that being said, I would like to start with the sea ice impacts now. And this is based on the time series of sea ice concentration and cyclone occurrence at each grid cell of the data set. And I made a small illustration here so that you can understand what we were actually doing. So for each of the cyclones or cyclone clusters, we just calculated change in sea ice concentration from one day before the cyclone arrived towards the end of the event. So in this case, it could be something like minus 22%. And then as a second step, we removed the seasonal sea ice concentration trend by just subtracting a reference, which we calculate at the same grid cell, but from time steps when there was no cyclone present at this grid cell, so that we just know what would we usually expect over this time period of 2 weeks if there wouldn't have been a cyclone present. And then we can average this for all the cyclone cases to get the mean impact at each location in the Arctic. And this is what you can see here for both subsets of cyclones. So to the left, this is the cyclone clusters of 2 or more storms. And then here in the center part, these are the regular solitary cyclones. And I think what these plots tell us is that we have all these blue colors here indicating a sea ice concentration decrease relative to the non-cyclone conditions for both types of events. But this is pronounced stronger for the cyclone clusters than for the solitary cyclones for many regions. I highlighted some of them here. And in general, you can also see that all these cyclone impacts, they are mostly limited to the marginal seas of the Arctic in the cold season, because in the central Arctic itself, where the ice is just very compact, we do not have significant cyclone impacts anyway on the ice cover. And yeah, as I said before, we also wanted to analyze if there are recent changes in the way that cyclone clusters impact the ice. So you can see here the plot that you already know, cyclone clusters 2000 to 2024, and next to it, the earlier period of 1979 to 1999. And this actually shows some interesting differences, specifically in the Barents Sea region. There, we earlier had only a very limited region here in the south of the Barents Sea, where we had strong impacts on the sea ice cover. And nowadays, basically this whole domain here is strongly impacted by the cyclone clusters. And before I propose an explanation for that, I would like to show you the warm season results first. I would just directly bring this up here. Again, we can find some interesting differences for both subsets of cyclones. In the middle here, the solitary cyclones, they really only have an impact on the sea ice cover in this quite narrow region here, close to the ice edge in the Barents Sea. And in contrast to that, the clusters of several cyclones, they also have an impact, for example, in the Beaufort Sea or at these spots here alongside the Siberian coastline. And what I personally find very interesting about this plot is that, to me, it suggests if we have, let's say, two cyclones following on each other quickly, it doesn't simply mean we have just double the sea ice impact, but we could also find regions where one single cyclone is apparently not strong enough to have an impact at all, but two of the cyclones can actually make an impact. So that's what I think is maybe quite interesting about these findings here. And then as a last point for today, also for the warm season, the comparison of the both time periods. And this actually reveals that all these spots that I highlighted here, they are, again, mostly found in the time period 2000 to 2024. And in earlier times, we didn't have such a strong impact of the cyclone clusters on the ice. And yeah, as I said, we also have kind of an explanation for that. We did some further analysis that I will not show today for the sake of time. And there we found indication that the changes in the sea ice cover itself drive this amplification of the cluster impacts because the sea ice got thinner and less concentrated on average, and that means it is easier for the atmosphere to have an impact on the sea ice. The clusters itself have not really changed too much, so this is our proposed explanation as of now, but we are working on to reveal some further details on this, since this is kind of ongoing work. But for everything that I've showed today, I would like to provide you a quick summary now in the end, and I prepared kind of 3 take-home messages for you. So the first one is that cyclone clustering is something that actually is not a rare event, but instead it occurs quite frequently in the Arctic. Specifically in the North Atlantic storm track region, actually more than half of all the cyclones are part of such a cluster. And then the second message is that whenever this occurs, it is usually related to a stronger temporary sea ice concentration loss than we would expect for only a single cyclone event. So it is also quite relevant for the sea ice cover. And then the last point is that we have a recent intensification of these cyclone cluster impacts on sea ice when we compare it to earlier decades, presumably related to the ongoing sea ice decline in the Arctic. And with that, I've reached the end of my talk, so thank you for your attention, and I'm happy to take questions.
Thank you, Lars. We have time for questions for Lars. Yes, Ethan?
Hi, Lars. Great talk. Thank you. My question is whether you have a sense of the sea ice concentration changes, if they're mostly dynamic or thermodynamic in nature, and what mechanisms you think are at work when it comes to the greater impact from cluster cyclones in some cases.
Yeah, good question. Actually, we have done some modeling work to disentangle this a bit. for this case that I showed in the very beginning. So statistically, I cannot really say it, but for the specific cyclone cluster I showed in the beginning, we saw that it was very strongly dynamically dominated. But this was, of course, in winter, and I would assume that in summer it can look different, that also thermodynamic impacts on the sea ice cover, maybe even some upwelling in the ocean if the conditions are suitable, could also play a role. So, yeah.
Thank you. Paul, you had a question.
Sure. Thanks very much. Really interesting. And I wanted to know if those clusters you're seeing, are those like wave packets? I mean, are we actually seeing like a series of cyclones that are sort of spun up by the kind of same large-scale system, or are they just coincidentally happening to cluster together?
I would strongly assume that it's the first case, but I have to say that I didn't yet look at the large-scale drivers. But that would definitely be something that we want to have a look on as a next step. But from the cases that I looked at, I would say there are common drivers, and it's not like randomly coming from different directions.
Thanks. Camille, yes.
Thanks a lot for the talk. You cluster your cyclone by basically the occurrence, but not really much by their characteristic. And I kind of thought that the cyclone were becoming more numerous, but also more intense. And do you see any like correlation between their impact and their intensity or their size? Or, I mean, you would guess that would have an impact as well, but is it like secondary compared to the clustering, or is it like of primary importance?
Very good question, yeah. So far, the clustering itself, we only do it by the occurrence, as you said. But then afterwards, we also analyzed the properties of the clusters we detected and also of the solitary cyclones we detected. And specifically, the intensity of the cyclones is very important for their sea ice impact. What we found, though, is that if we have two clustered cyclones of, let's say, average intensity, they can actually result in the same sea ice impact than one very extremely intense cyclone. So this is maybe something how we could put this together, that maybe two clustered weak cyclones are more likely or easier to occur in the Arctic, but can have the same impact as one record-breaking event. But I'll have to follow up on that in more detail before I can make reliable statements about that.
Thank
you. It's a really great talk. And my question sort of be asked already, but just a follow-up on that. Since talking about the characteristic of the cyclone, I'm wondering if the clustering you're looking at, the cyclone is originally more like original over Arctic region, or is it like the cyclones like moving from lower latitude then to the more high latitudes? Because it seems like it have some different like heat transport regarding that.
Yeah. I would assume also I didn't look at the origin of the cyclones yet, but it's a very good point. I will try that. But since we found most of the clusters across the North Atlantic storm track, I would assume that it's probably something that rather moves into the Arctic, but I would have to double check.
Yeah, another question is more technical. So like in your like clustering technology, like how sensitive that is to like your 48 hours window?
Yeah, actually we started with that based on some previous literature, but we have the database available for all the time gaps we want. So an undergrad student coded that in a way that we can just pick the time gap we want and we get all the clusters. So we also plan to test the sensitivity of our results. Yeah.
Thank you.
Are there other questions for Lars? Otherwise, I guess everybody's ready for the break. Let's thank Lars again and all the speakers in the session.